Well, hello and welcome to this NASA Earthdata webinar about monitoring inland and coastal water quality across the entire U.S. with NASA's STREAM. I know I'm excited to learn about STREAM today, and I hope you are as well. Thank you so much for being here today. Just a few words before we begin. As you might have already noticed, the chat is open, so feel free to engage with your fellow attendees during this event. If you're going to interact with others, we ask that you do so in a respectful and professional manner. Next, AI bots like note-taking tools are not permitted in NASA meetings. That's not our rule, that's a NASA policy. If any are detected, we'll have to boot those from this meeting. That being said, that brings me to my next point. The recording of today's webinar will be publicly available in a couple days, and you'll be able to find it on the Earthdata website. And watch your inbox because you'll receive an email when the video is available as well. And finally, a Q&A session will follow today's presentation, but make sure you post your questions in the Q&A tab on Teams, not in the chat. You should see a Q&A icon in the meeting toolbar at the top of your Microsoft Teams window. With the announcements out of the way, I'm happy to turn things over to William and Ryan.
Hi, everyone. My name is Ryan O'Shea. I'm a member of the Freshwater Sensing Program at Science Systems and Applications, Inc. We're a contractor, and we're currently funded by NASA as well as the USGS. The Freshwater Sensing Program consists of myself, Will Wainwright, who will be presenting the second half today, Akash Ashapur and Arun Saranathan, and it was formerly headed by Nima Palavan. Shown in the background here is a pretty cool image of Severn Sound with some interesting optical complexity. You can pull it up in our Stream website using the QR code in the top left if you want to play with the tool while I go through my slides. So why develop STREAM? Well, the motivation was to be able to study harmful algal blooms on fine spatial scales, because these harmful algal blooms can produce toxins, cause hypoxia, and generate scums. These can go on to damage the ecosystem, public health, recreation tourism, as well as water resources. Water quality managers would like timely, representative sampling so that they can quantify and characterize these blooms so they can better issue warnings and implement remediation efforts. The highest accuracy measurements typically come in situ. However, those have large resource constraints associated with them due to cost, time, and weather conditions. So water quality managers can turn to Earth observation to better inform their in-situ sampling and remediation efforts. We have a wide range of satellites available that provide temporally and spatially consistent observations so that they can simultaneously estimate biogeochemical parameters and IOPs. So I talked about how there's a wide range of different sensors available, but just if you don't have the background for what sensors are available for aquatic remote sensing, I'm quickly going to take you through sort of a timeline and general overview of a lot of the sensors that we support. One of the longest running is MODIS. It's been around for about 26 years as kilometer scale imaging, multispectral resolution, and it allows us to have basically climatology of many large aquatic water bodies. We have MDNs available for that. We also produced MDNs, the machine learning model that we use for VIIRS. It has about 750 meters spatial resolution and again daily temporal imaging, so we can combine those to get really high temporal resolution but at coarse spatial scales. With STREAM, we were interested in smaller inland water bodies, so we leveraged Landsat 8 and 9 as well as Sentinel-2A and 2B. So these are finer spatial scale resolution down to about 30 meters, but each of them has about 5 and 8 day revisits. But when you combine them together, you can get down to about a 4-day revisit. We also have models for Sentinel-3, which has higher spectral but slightly coarser spatial resolution than Sentinel-2 and Landsat 8. There's also a wide range of hyperspectral instruments available that we've developed models for. Some of the more recent ones include EMIT, which has about 90 meter spatial resolution, but intermittent spatial or temporal coverage, and PACE, which has kilometer scale spatial resolution, but daily coverage at hyperspectral resolution. So we're going to be adding that in to increase the accuracy of our products and be able to achieve daily temporal coverage. We're also going to be adding in Landsat next when that becomes available. These are all radiometrically capable sensors that provide daily observations when combined together with different spatial and spectral capabilities, with the basic idea that we can combine them together to get a better understanding of the inland and coastal waters globally at the highest spatial, spectral, and temporal resolutions possible by combining them. However, since they all have different spectral resolutions, we really need a robust workflow to produce these seamless products over fresh and coastal estuaries. That's where Aquaverse comes in. Aquaverse is our robust framework. It's an aquatic inversion scheme for the remote sensing of fresh and coastal waters. We start at the top of atmosphere radiance, what the satellite sees, the light at the top of the atmosphere. Then we atmospherically correct it. So we remove about 90% of the signal just to get to the 10% that is the ocean color or remote sensing reflectance. This is done by Akash. Akash then pushes this ocean color signal onto me. I apply a different set of machine learning algorithms to estimate biogeochemical parameters. This is things like chlorophyll, which serves as a proxy for aquatic plant biomass or phytoplankton biomass, and is generally a proxy for aquatic ecosystem health. We also have other proxies like total suspended solids and color dissolved organic matter. I then pass these products on to Arun, who generates uncertainties. These uncertainties can be used sort of as a confidence metric. They basically say how confident the model is in its own predictions, and they can be used to block out any regions that the model isn't confident in its predictions in. We then pass all of our products on to Will. Will runs Stream, which is going to be covered in the second half of this presentation. It's our stakeholder access. Again, you can access it at the QR code on the left. We also have done similar training from NASA Earthdata. So there's a little bit higher coverage of our validation there if you have interest in any of the validation routines for these models. So we're going to start off with atmospheric correction. Atmospheric correction, again, is the most challenging part. About 90% of the signal over aquatic regions comes from the atmosphere and only about 10% for the water. So getting that right is essential to being able to actually calculate what is in the water, what the constituents are. We atmospherically correct by first determining a representative data set of about 1,800 measurements that we pull from existing datasets like GLORIA, as well as the AERONET-OC network. We then simulate about 400 million different TOA reflectances by varying the geometry, aerosol models, aerosol optical thickness, and water vapor, and running it through a radiative transfer model. We take those 400 million different TOA reflectance RRS pairs, and we can resample the TOA reflectance to the satellite's spectral resolution, or with the relative spectral response function. We can then do Rayleigh and gaseous corrections similar to what L2GEM does, and finally apply an inverse model that goes from ρRC to the downstream RRS, which is specifically designed for these inland and coastal waters. And finally, we can go on to testing and validation. With the remaining data that we left out of training, we can then do some testing and validation and compare against a suite of alternative atmospheric corrections from Acolyte to OC Smart to CDAS and compare them to Aquaverse ours. And we can see that with bulk validation statistics, we're better able to retrieve in both inland and coastal waters and across the blue to red wavelengths. Also, qualitatively, you can see that spatially we're able to retrieve more valid pixels, and in general, it spatially lines up pretty well with alternative atmospheric correction approaches like L2GEM, and you get similar results between both OLI as well as MSI. We submitted this and actually recently had it accepted in a publication, but we're going through major revisions right now, and that should be out in the next, hopefully, month or two. Okay, so we just went through atmospheric correction. Akash derives the ocean color signal. He hands off to me, and then we do some inverse modeling and uncertainty products. How do we do that? Well, we need a really large representative data set to be able to derive the biogeochemical parameters in a wide range of different optically complex waters. So we've assembled about 10,000 RRS pairs with different biogeochemical parameters, including chlorophyll-a and TSS from around the globe, though it is dominated by North America and Europe, though we're slowly filling it out to other regions as well. Shown on the right are histograms of chlorophyll-a, PC, TSS, and CDOM for our in situ training data set. You can see we have about 5,000 measurements of everything except for phycocyanin, which we only have 1,000 measurements for. It's a little bit limiting for phycocyanin retrieval, but it represents a wide range of different conditions for chlorophyll-a, TSS, and CDOM. So we have a really representative data set. Now we need a machine learning model that works well in these optically complex inland and coastal waters. What we found works really well is what's termed mixture density networks. It's basically a standard machine learning model on the left. So you input some ocean color signal. It goes through some feature engineering like line heights and band ratios. You normalize it and scale it between -1 and 1, and then run it through the regular weights of a standard neural network. But what sets mixture density networks apart is that the output layer is a set of Gaussians. These Gaussians each have a probability, a mean, and a standard deviation associated with them, and they're trying to represent the probability distribution function of the output variable, let's say chlorophyll-a, given the input of the ocean color signal. And this is useful because not only is chlorophyll-a varying in the water, but also TSS, as well as absorption properties due to CDOM and non-alkyl particles. So there can be a wide range of different combinations of these different variables for any input RRS spectrum. So it's really good at solving this non-unique inverse problem. So let's say we take a ocean color signal and we propagate it through a few different algorithms. One of them is OC3, which is shown as the blue dashed line. One of them is a standard neural network shown in the red dashed line, and we have the in situ value shown as the black dashed line. With mixture density networks, we actually get a set of Gaussians, again, each with a mean, standard deviation, and probability, and we can select the most probable value instead of the average, which standard machine learning models do, to get a better estimate of the actual in situ concentration. Okay, so we have the model picked out, and we have a large data set. We can then do in situ training, which is shown in the top graphic, for a specific sensor. So on the top left, you can see the mixture density network achieves about 30% uncertainty across maybe 4 orders of magnitude for chlorophyll. And there's a couple alternative algorithms that achieve about 50% uncertainty. This is in the ideal scenario where we do a 50-50 training split, so we don't actually expect it to work this well on satellite data. We can also do something else that's called a leave one out validation, where we take each of the 42 different regions, leave it out of training, and train a model on the other 41 regions, and then see how well it does in the left out region to get an estimate of the accuracy for regions that aren't represented in our data set. Now we can see we get about 50% if you average over all of the different regions. So for out of training data, we could expect maybe for 50% accuracy. But one of the major limitations is actually the atmospheric correction uncertainties, which go on to limit water quality parameter retrieval accuracy the most. If we get matchups between satellite overpasses with in situ concentrations of chlorophyll-a for the MDN shown on the left, for different atmospheric corrections like acolyte on the top and CDAS on the bottom, you can see that it substantially can limit the accuracy of the model, as well as the alternative algorithms. We do have Python tutorials for these models at the QR code as well. You can see that they're also relatively well harmonized between the different sensors, though there are some different variations between Landsat 8 and Sentinel-2, which are the 2 sensors we use for stream. So I've shown you these products that we can generate: chlorophyll-a, TSS, CDOM, and phycocyanin. They generally are spatially quite coherent, and they line up with the literature, as well as a large amount of validation work that we've done in both publications as well as prior presentations. But we can also generate uncertainties leveraging that mixture density network architecture that we showed before, where we can look at the distance between the different Gaussians to start to estimate the uncertainties. And those uncertainty maps are plotted on the right. Okay, so I just really quickly took you through atmospheric correction, as well as inverse modeling and uncertainty production. And now we're ready to pass these products on to Will, and he can talk about Stream as well as stakeholder access. So how you guys can use these products. Thanks. Will, I'll turn it over to you.
Thank you, Ron. Give me a second here to share my slides. So, like Ryan was saying, from the many different satellites and sensors that we have developed models for as a team, we've selected, at least for now, Landsat 8 and 9 and the Sentinel-2 family to be the primary data sets that we feature on Stream. And the reason for selecting these in particular is their high spatial resolution relative to some of the other satellites that are on offer, as well as the fact that they both have many of the bands that we need in order to do accurate water quality parameter retrieval. So the main differences between these two, Landsat 8 and 9 have a fixed 30-meter resolution across all of their bands. And between the pair of them, they have an 8-day revisit rate for a given scene that you're looking at. Sentinel-2 has varying resolution depending on the band. It's either 10, 20, or 60 meter. For the purposes of what we do on Stream, we actually resample everything to 20 meters, kind of take the average of everything. And then actually with Sentinel-2C now having launched I think a year ago, the 5-day revisit rate is it's more like 2 or 3 depending on where that Sentinel-2C overpass lines up in the cycle. A and B will alternate in kind of a 5-day revisit rate, but C is a bit of a wild card between the two. Stream is both a website and an API. The primary tools on Stream are the interactive map and the newly introduced time series tool. The map lets you view the mosaicked tiles from a given satellite's overpass in context with each other. So normally if you were to access a scene from, let's say, Sentinel-2, you would see one grid square and, your water body may or may not fit into it. For looking at something like Chesapeake Bay, you may have to tile together 2, 3, or 4 satellite overpass tiles in order to see the full water body. And so what Stream does on the interactive map is it tiles those together, it mosaics those together, so you can see all of the water quality estimates for a given day's overpass. Stream also has an archive where you can download those individual squares, those full resolution geotiffs. It's been operating live doing daily processing since June of 2024, and we've slowly increased the coverage of what's provided. So many large and prominent water bodies in the US began their coverage in June of 2024. We rolled out full CONUS coverage for Sentinel in early 2025. And at the start of this year, we rolled out full Landsat CONUS coverage as well. Stream is also powered by an API that you can interact with scripts. We have a fleshed out API documentation that I'll touch on at the end as well. And I'll touch on the time series tool too. In lieu of doing a live demo here, I've kind of scripted out what you would see if I were going through a demo. And I'll also try to provide these slides to the Earthdata team so that they can include them alongside the recording if you guys wanted to use this as kind of a follow along. But you can find Stream a couple different ways. I think Ryan had a QR code at the start, but you can also search up for NASA Stream water quality. This is what the link looks like. And on the homepage of Stream, there's a couple different ways to get to the map. You can either hit explore the map or click on the map there. There's also the API documentation here. Once you're on the map page, you can do a couple different things. There's a panel on the right-hand side, and at the top of that panel, you can enable the different satellite grids. This is mostly just for seeing what we cover and what we don't. So if you enable the Sentinel satellite grid, you'll see a large lattice of squares, and these are where the European Space Agency breaks. I think they're using a grid called MGRS, but they break the map into different tiles, and the ones highlighted in blue are the ones that are part of the daily processing on Stream. You can zoom out. We have select coverage outside of the US as well. Alaska and Hawaii are also included. Landsat has a similar grid, and that'll show as orange squares. And then if you want to quickly navigate to an area of interest, there's a search bar. So here for this example, I'm typing in Mono Lake, and that takes us over to Mono Lake in California. Once you're there, you can just click anywhere and drop a pin. That will tell you the lat long of where you have clicked. If you're trying to find a specific point, maybe you have a buoy or some other in situ data that you want to match up, or you just want to get data at a specific location. And options under that pin are to search coverage by a particular satellite and to view the time series. For now, we're going to look at searching for the coverage. That will take you over to the archive search results page. You have a column for the date as well as the day of year if you prefer that format. Next to that, you have this particular satellite that result is from, Sentinel-2 A, B, and C, and the products that are available. Almost always, the products are always going to be the same. For both Sentinel-2 and Landsat, we have the chlorophyll-a concentration, the total suspended solids, the Secchi depth, and the RGB true color composite, which is kind of just what you would see, what the scene looked like on that day. So here I've gone and picked a scene that I thought looked pretty interesting, especially in the RGB. So I scrolled down to 2025, November 6th. That happens to be a Sentinel-2B scene. And clicking that takes you to all of the data for that scene. So here we have the individual product TIFFs at their full resolution. Here it's resampled to 20 meters. And we have the chlorophyll-a, TSS, Secchi, and the RGB composite. And you can see the file size as well as there's a zip for all the products. But also on the left, we have a link back to the map. And what this will do is it will preload the map with the layer for the date and the product that you've clicked on. And remember that these are mosaiced together. So even though you are getting back to this map by clicking on a point in Mono Lake, any other scene that was viewed by Sentinel-2 on that day will also show up. So here we've just zoomed back into Mono Lake, and we can see kind of a swirl in the pattern. A couple different things you can do once a layer is loaded in on the map. As you hover your cursor over pixels, you'll get a live pixel readout you can kind of see on the right. Above that, you'll also see the coordinates of the pixel that you're hovering. And then if you expand the options for the layer that's under active layers, you can change the color palette as well as the minimum and maximum chlorophyll values to set that palette range across. You can also set the opacity of a layer if you want to see things under it, and that becomes especially handy when you add multiple layers. Here, it's already pre-filled the satellite and the date, so I can just go ahead and select another product, for example, the RGB. And then if I want to make sure that the chlorophyll is showing on top of the RGB, then you can drag the layers to reorder them. You can also click to quickly hide and show layers, as well as expand their options to change things like the color palettes and opacity individually. Going back to the start where we're just kind of dropping a pin on the map, the The other option is to view time series. And what this will do is plug in those coordinates that you see into the time series page. And it'll link you there. You can also get to the time series page by just clicking the time series button at the top of the navigation header. If you just wanted to enter the lat and long yourself. Once you enter those in, you can select the start and end date. Right now, for most data on stream, that's going to be sometime in 2024 to present. We're hoping to soon expand the back catalog of data we have, so that you can see trends over more years for some of these sites. You can also select products that you want to generate a plot for, and the radius over which you want to take a median. So for here, we're taking a 90-meter median radius. And then you hit generate plot. I've got a still on the right of what that looks like, but it takes, depending on your machine, a minute or so to generate this plot. And then once you're looking at the time series, you can hover any of these points, and it will give you a live preview of the RGB for that tile. If you wanted to download this data to make your own plots or do some kind of analysis of it, there's a download CSV button, and that will download all the data points in these plots, as well as include, you might see some of the points are actually in X. That either means that the time series tool detected that there was maybe a cloud in the way, so that would have a flag in the RGB column, or it was deemed to maybe be too extreme of a point relative to some of its nearby neighbors, and so it's got a flag in its respective product column. Finally, touching on the API use again, you can see you can get to the API documentation from the homepage, and we have a way for you to download the API document as a YAML format that's OpenAPI compatible. You can also scroll through and interact with it on the API documentation page. And finally, I've created a Python example script where it will go through and download for like a set date, range, and tile. And I've tried to make it very easy for you to edit. These are the tiles I'm interested in. This is the date range I want the data for, and these are the products that I want, and it will just download them all to a local directory for you, those full resolution geotiffs. Some of the future products and features that we're working on for Stream, one of the most requested, especially for applications and things like aquaculture, has been sea surface temperature. This is something that we're going to be deriving from Landsat 8 and 9 tiers. Another highly requested feature is just increasing that temporal resolution. Having revisit rates more than 5 days or 8 days, like it is for Landsat and Sentinel. The only real way for us to do this right now is to kind of come at a trade-off with spatial resolution. So PACE and Sentinel-3 have a much higher temporal resolution, but they have a bit lower spatial resolution. So we'll kind of fill in the gaps that way. We're also looking at doing domain adaptation to kind of harmonize the results between these sensors. And then finally, some overhauls to the interactive map. Having a simpler way to just navigate between days, like next and previous. Having it automatically load the RGB for that selected date, so you can just very quickly see, hey, it was cloudy this day, let's go previous. And then having a quick way to toggle the products without necessarily having to leave the map. Those are some of the things that are kind of on the docket for us already. Otherwise, I think we're about ready to wrap it up and head over to Q&A. There's a QR code here for Stream. Again, just example of how to find it. And yeah, did you have anything else to say, Ryan?
No, great wrap up, Will.
All right, thank you.
All right, we'll move into our Q&A session today. And just a reminder to use the Q&A tab you'll see at the top of your team screen. And that's where you can post your questions. I see a couple in there already. But if you've got questions, post them in there now, and Will and Ryan will take care of those. All right, go for it, guys.
So we had one question earlier when you were presenting, Ryan. I don't know if you had a chance to look at it.
The question was, how will NISAR data help freshwater and coastal monitoring? You responded that it fills a different role in satellite monitoring as it does not have the passbands to directly estimate water quality parameters like chlorophyll-a concentration. We'd be very interested to see how it serves as an additional tool. And yeah, from my brief reading on synthetic aperture radar, I think it could be used to measure changing water levels and seeing maybe how that correlates to changes in phytoplankton blooms. We do a lot more of the algorithm development than applications, though. We don't currently have plans to integrate SAR into our framework. There's another question. Let me preface this with awesome. A 50% accuracy on leave one out validation was cited. How was accuracy defined? The accuracy metric we use is called median symmetric accuracy. I linked to our internal paper, our published paper from Remote Sensing of Environment 2023, where I think it covers that leave one out validation as well as the metric we use. Median symmetric accuracy does a better job of being tolerant to outliers, so it isn't affected very much from significant outliers, and it also weights under and overestimation similarly, but you can read about it more from the papers linked there. Is that plus or minus 50% of the predicted value? To give you scale, so we do this in log scale, 100% error would be a factor of 2 over or underestimation. So I think 50% then correlates to about plus or minus 50% under or overestimation. So half of the data that we would predict would be in that range of plus or minus 50% from the true value. The QR code, sorry, which QR code would you like?
I just linked stream directly. I don't know if they were looking for like a specific plot QR code or not, but
yeah, I might have gone a little overboard on the QR codes in my presentation, but if there's a specific one, we'd be happy to link that as well. Another question is, how are lake bed or stream bed reflectances affect differentiated or accounted for from water body reflectances? So currently we do not have any training data from optically shallow environments where we get reflectance from the bottom. That said, we have submitted some proposals because we are interested in doing that same framework that I went through, where we simulate the remote sensing reflectance and go to top of atmosphere. We're interested in also including the bottom reflectance as well. We have some simulations of that, including bottom reflectance with the aquatic signal and then propagating that up to the atmosphere. But we have unfortunately not yet been funded for this. It would be great for us with this high spatial resolution to be able to remove that as well and be able to quantify how all our algorithms do in those optically shallow environments, particularly for like island nations. But unfortunately, we just haven't gotten our proposals funded for that.
I think there's another one in the Q&A tab. Are there water resource managers or other end users using the tool in their workflows at this time?
Yeah, so we're trying to get it taken up by a few different organizations. One of the bigger ones that I was working with was Remarco. It's a group of Caribbean as well as Latin American countries who are interested in using potentially our MDNs or stream for evaluating eutrophication. It's still undergoing validation, though the initial results look quite promising for the accuracy from stream from that region. Another region that was interested in our products and where the initial validation data looked really good was the inland waters of South Africa. We have a collaborator there who was trying to implement our MDNs for monitoring these waters for generating reports. We haven't yet had somebody fully take it up, though, for monitoring purposes. So actually, we did have another user leverage it in Colombia as well, specifically for a region that we had validated for them, inland coastal water.
Yeah, David gave us an example of a lake that might be good for using in that updated model of bottom effects. Are you familiar with that acronym, Ryan?
Digital elevation map.
Right.
Basically a depth map. I'm guessing. We haven't really looked into it. Yeah, it's possible that leveraging that depth map would help with removing the bottom surface effects.
There's a lot of ancillary data that goes into improving the accuracy of especially our atmospheric correction models. Stuff like water vapor in the air, oxygen, like ozone concentration, wind speed. I can imagine that if we updated the model to account for stuff like bottom effects, having the depth of the subsea surface would probably be a pretty important ancillary. And so I do think it would be helpful.
Yep. Another question is, are there any sites in India? I don't think we've added any. There is a map where you can see the currently supported sites. Maybe if you want to link to it, will. But we are able to add sites as well if there's like a specific test case or area. We can't add a ton because we have some computational limitations, but we are interested in testing it out, especially if there's regions with in situ validation data. You can just send either of us an email.
Yeah. And one thing I was talking about in the soon to come to stream, when we add PACE and potentially Sentinel-3 ULCHI, those have a much coarser resolution. And so we should be able to support many more regions, if not the entire globe, with PACE.
Yeah, that's a great point, Will.
So
Yeah,
you will be getting daily water quality maps for the whole globe from PACE. The trade-off is just a bit lower resolution.
Yeah, a fair bit.
Yeah.
Yeah, David, that sounds like a great opportunity. If it's not already added in, we can try to add in Torch Lake as well. Though it's probably covered because you said it was in Michigan, right? Is golden brown algae, I'm sorry, is that a phytoplankton or is it a benthic algae? I see. Yeah, we usually more estimate the concentration of the concentration of chlorophyll in the water column. But it might be an interesting application to look at algae on the benthic algae as well.
A couple more questions in the Q&A tab.
Oh.
Any plans to include eco-stress radiometer data?
We do not currently have plans or funding to include eco-stress.
I see there's a question about Sentinel-1 going offline. We're not currently using or applying Sentinel-1 data, but it is always sad to see satellites decommissioned. And even if, I don't know, something happened and Sentinel-2 unfortunately had to go offline, we aren't planning on removing any existing products from stream. So it might impact future operations. You'd obviously lose that data set going forward, but everything on stream would remain. David, this does sound like an interesting application. If you wanted to shoot Ryan and I an email and we can follow up on this more, I think I'm interested in seeing where this can go.
Yeah, I'd be happy to chat about it further.
All right. Well, we have come to the end of today's presentation. Of course, we want to give a big thanks to our presenters for taking the time to walk us through everything today. If you'd like to share any feedback with us, earthdata-support@nasa.gov is how to do that. Thanks again to everybody who attended live today. Again, the recording of this event will be publicly available soon. So watch your email for that or look for it on the Earthdata website. And while you're there, be sure to check out all of our upcoming webinars and freely available learning resources. And we hope you'll join us again for another NASA Earthdata webinar.